I'm going to try surface mount reflow soldering on this hot plate sent to me at no cost by Banggood to try out. This one is 20 by 20 centimeters. They also have a 10 by 10 centimeter, but these boards are just under 10 centimeters wide. So I figured if I have a 10 by 10 board at some point, I'd like a little extra latitude. Plus, this allows me to work with larger boards. Even if I'm not designing them, I may have a big board that I need to heat up and remove components from or rework. The reason to use a hot plate is when there's a circuit board, it can be preheated either to remove bulky components that might be soldered into the ground plane and it's better to heat the whole board. Then you can just add a little more hot air and remove heavy components. And it's a good idea to have the whole assembly up to a uniform temperature so that when you do apply hot air for reworking, you're not creating a large thermal difference which could damage components, maybe warp the board. But another use is for reflow soldering in the first place. When you have a PCB that you want to put solder paste on, you can put it on here, bring this all up to temperature uniformly until the solder paste melts and you get a soldered circuit board. Using the hot plate for soldering is only recommended for hobby work or small batch prototyping. Before turning this unit on, I'm not going to do a teardown. There's other videos that show what's inside, but I will just check for grounding. So the top plate is grounded. And I see there's a little paint scraped off this corner on the metal here. So that's also grounded. If I turn this on its side, there's screws mounting these rubber feet to the bottom. So that's grounded. And I think there's a little paint worn off right here. So this is also grounded. So when I plug this in and power it up, it will show the set temperature and it will start ramping up to that temperature. So I can press this star button and choose, let's say I just want to go to 100 degrees. And now it's going to go from 40 up to 100. There's this calibration potentiometer here. So if you were to put a thermocouple up here and measure the temperature and see that the display is off a bit, you can use a screwdriver to adjust this pot, try to get things to match up on the display. Let's characterize the unit's heating and cooling rates just with a thermocouple on the hot plate surface directly. I'm going to put one thermocouple right in the center, which is going to be the top reading on the meter, and another off into the corner so I can see if the temperature looks relatively even across the surface. Then I'm just going to set the temperature and let it ramp up a couple hundred degrees, and then let it cool down on its own, see how long it takes. Both of these thermocouples are only a couple of degrees apart, so that seems good. Surface mount reflow soldering in a production environment is usually done in a proper reflow oven. Whether it's a conveyor belt system like this one, where the board goes through and at different points along the path, the temperature can vary, so you can have cooler and then hotter and cooler again. Or it could be a single position toaster oven type approach where you just ramp the temperature itself up and down while the board stays stationary. But the temperature will follow a reflow profile similar to this. Depending on the kind of board and the kind of solder used, there will be a ramp-up portion of the profile where the whole assembly, including the board and all the parts on it, come up to a certain temperature at a controlled pace so that we don't thermally stress any of the parts, and it reaches a temperature just below the solder melting point and may stay there for a while to allow everything to reach that temperature and also allow any chemicals to start activating in the solder paste. Flux can start doing its work to clean and prepare the solder balls in the paste and the pads on the board, and any volatile compounds can evaporate away. And when everything is up to stable temperature, the temperature increases beyond the solder melting point and reflow occurs, and then the temperature is decreased, which occurs ideally at a faster rate than it had increased in the beginning. And having a faster temperature decrease gives a better solder connection. After measuring the temperature on the hot plate directly, it heats up between about 36 and 41 degrees per minute, or around 0.6 to 0.7 degrees per second. After turning off the hot plate at a couple hundred degrees and letting it cool down on its own, it's cooling down a lot slower than it was heating up. It's about 8 degrees per minute, or 0.13 degrees per second. And the more time passes, the slower it takes to cool down. Since the soldering is taking place on top of an FR4 PCB, I'm going to do another test to see the temperature directly on the PCB surface, which is the temperature the solder paste will be exposed to, and compare that against the hot plate directly. There's other soldering profiles as well, where it just increases steadily up to this maximum temperature without a dwell period. And for the specific solder paste I'm going to be using, it has a reflow profile that looks more steady, increasing up to the peak. And this may be more suited to hot plate soldering because unless we sit there turning the switch on and off or changing the temperature by hand, if we turn the hot plate on and leave it running, it's going to ramp up in temperature to whatever peak, and then we can turn it off and let it cool down. This specific solder melts at 138 degrees Celsius. So looking at this profile, by the time we get up to about 138 degrees Celsius, we're ready to boost the temperature and do the reflow of the paste. So it looks like we can just turn the hot plate on with a board on it, let it heat up until the solder melts, and then cool it down. I'm going to put a couple of pairs of metal pliers on top of the hot plate when it's time to cool the PCB. Looking at the results of measuring the temperature directly on the PCB surface, that temperature is lower than the temperature directly on the hot plate, of course, because the PCB needs time to heat up to the hot plate temperature. So as the hot plate itself is rising in temperature, the PCB will be rising at about the same rate, 0.6 degrees per second, just at a lower temperature because it needs more time. So it looks like just putting the PCB on this hot plate and letting it heat up, it will only take a couple of minutes to get up to the target temperature at a controlled, relatively steady pace, and we should be able to successfully reflow this board. But we do need to cool down the PCB a lot faster than just letting it sit on the hot plate surface. And when I did a test run of this, I was able to cool the PCB about 1 degree a second, and then as time goes on it takes longer to cool the board, but this should be good enough to mimic the cool down portion of the solder reflow profile. In order to test the hot plate for reflow soldering, I had a PCB made along with a solder paste stencil to make it easier to apply solder paste, although some people successfully just apply it straight out of a tube. And I need to align the stencil to the PCB so the openings match where I want the paste to go. And to do this, I taped down some spare PCBs to get everything aligned and allow me to have a surface to tape the stencil to, and then I can just flip it up and down and remove the PCB when done. I applied the paste directly from the syringe without using a needle because I didn't need precise placement. I used a semi-rigid plastic card as a squeegee so that I could pull the paste along at whatever angle made sense, trying not to miss any pads or remove any paste that was already on the pads. It's easy to rip up the work you've already done, so it took a few tries, but eventually I got it all covered. But it also looked like I made a bit of a mess and completely bridged over a blob of solder paste on all the small pads of an IC on the left of the board. I was hoping the reflow process and the solder mask on the PCB would keep the solder on the pads where it belongs, and if not, I would just repair any solder bridging after. I used 99% isopropyl alcohol to clean the solder paste off the stencil before it dried, making sure to get both sides and clean out anything in the cutouts. Then I manually placed all the components on the board with tweezers, not worrying too much if they are straight or centered, because during reflow, the surface tension of the solder paste will pull them into position anyway. When the board was ready to be soldered, I attached a thermocouple to the hot plate and another to the PCB surface, although it may not have been taped down perfectly, so the reading may not be perfect. After 3 minutes, some areas started to reflow, and by 4 minutes, it looked like all the pads were soldered. So I placed the board on the 2 metal pliers sitting on the hot plate to allow the board to cool and hope for the best. Overall, the soldering result looked good. Some components weren't perfectly aligned, but they were still soldered, and I couldn't see any bridging, including on that small IC. There's a few through-hole components, so I hand soldered those so that I could do a functional test of this circuit, which includes a boost voltage converter that takes 5 volts in and provides an adjustable voltage out beyond 25 volts. And everything seemed to work. I didn't have to make any repairs to the soldering, it just worked on the first try. For one-off hobby work or small batch prototyping to test a circuit design, the hot plate method seems to work well. And because of the way that the temperature ramps up on the hot plate, a lower melting point solder like the type I used, where it melts at 140 degrees Celsius, may be better suited for this approach. And it also seems that it doesn't matter if the solder paste is applied accurately, that all gets auto-corrected in the reflow process. Thanks to Banggood for supplying the hot plate at no cost for this experiment. Thanks for watching. I'll see you in the next video.